Algebra 1, Section 1-3. Let's talk about number sets. The umbrella term would be real numbers. And it's probably a term you've heard before. In fact, I would venture a guess that every number you've ever encountered in your life in a math class is a real number. You probably, and I'm not saying everybody, but probably you don't even know what a non-real number is unless you've done some type of standardized test, study, preparation for the SAT or whatever. Non-real numbers is something we don't get into until Algebra 2 at Forest Hills Northern. So I guess it'll just suffice to say that you should know that there is such a thing as a non-real number. Sometimes books will call them imaginary numbers, if you've ever heard that term. And that is a topic that you'll cover later in your math career. So these are all real numbers. And real numbers essentially can be broken down into two categories, either rational or irrational. Let's start with the irrational numbers. The irrational numbers are numbers that as a decimal do not terminate or repeat. Numbers like pi. Okay. Now I'm sure you know what pi is, at least starts with 3.1415926, et cetera, et cetera. If you looked at that decimal, what you would find is that it never terminates and it also never repeats. Never terminates or never repeats. And you can look online, and pi, they've figured out all the decimals to pi now into the millions. Okay, and you're not going to find the end of it because there isn't an end. It's going to continue to go forever. And I actually have an activity in my Algebra 2 classes where I show how it is that they can do that, how they can keep figuring out more and more digits of pi. It's not that they're getting more accurate at measuring around a circle, that's for sure. So take me for Algebra 2 if you want to learn about that. Just another example, the square root of 2. The square root of 2, if you did that on your calculator, it'd be 1.41. I forget what the number is actually, but it's a decimal that doesn't terminate and it doesn't repeat. The square root of 3 would do the same thing. Okay. Now, your book does not define it this way, and I'm going to define it the book way in just a second. But in decimal terms, that's correct. An irrational number is a decimal that doesn't ever terminate or repeat. Now, what about square root of 4? Well, the square root of 4 is 2. Okay. Well, 2 does terminate. Doesn't even have to repeat. It's a terminating number. If we simplified it, 2 would actually go here and here and here. We'll get to those in just a second. The square root of 5 would be back to the irrational category. And you're welcome to test all these on your calculator. Now, your book doesn't define it that way. Your book would say that an irrational number is one that can't be written as a fraction. Okay, and that's just as good of a definition. We have a feature on our graphing calculators, which you probably don't have, which is okay, but we have a feature on our graphing calculator that will turn a decimal into a fraction. And if I did the square root of 2 and got the decimal and then I did that function, it wouldn't give me a fraction because that fraction doesn't exist. Okay, do the same thing with pi. You can't turn that into a fraction. Basically a number over a number kind of fraction. Okay, if it's that, then it also is the non-terminating, non-repeating decimal, and it goes in the irrational category. Now, if a number is not irrational, then it's rational. Okay. Now this would include numbers like 5, 0, negative 3.2, negative 5,296.587. Okay. That's a terminating decimal, 0.587. That's to the thousandth, and that's done, and the thousandths place. And those are all rational numbers. Okay. If it terminates or repeats, just the same. Okay, so 2/3 is a rational number because 2/3 as a decimal is 0.66666, 0.6 repetend. It's a rational number. If it terminates or repeats, it's rational. Okay. Now, inside the rational numbers would be the integers, and integers, for whatever reason, is the one that students seem to miss. So I would like to put a spotlight on the integers, and they're easy, but don't overlook them. It's basically the whole numbers and their negatives. And we'll talk about the whole numbers in just a second, but usually students already know what whole numbers are. So 0, 1, 2, 3. So if you just take those and the negatives of those numbers, obviously negative 0 is just 0, but the negatives of all the 1, 2, 3, and you put that as a number set, these are called integers. Probably the most important one is integers. And then the whole numbers is just 0, 1, 2, 3, etc. The dot, dot, dot means etc. So 4, 5, 6, 7, 8, 9, 10 through infinity. Those are the whole numbers. Now, there is one more set if you read your book, and it's called natural numbers. Some books call them counting numbers. And I don't include it here because it's exact same thing as whole numbers except not 0. Okay, so the counting numbers or the counting numbers or the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so those are number sets. With that, then let's do a few examples. Because they'll ask us, but they'll give us a number and they'll say, what number set does this belong? Okay, so negative 13, it's terminating. Okay, so it's not irrational, so it's definitely rational. It is in the set of integers, right? If I kept going in the 0, negative 1, negative 2, negative 3, I would get to negative 13. Okay, it is not a whole number because it's negative. The whole number started at 0. So this we would say that it's an integer, it's a rational number, and it's a real number. Now, unfortunately, they didn't do that with the last one. They didn't say real, okay, because I guess they're just assuming you know that every number is real. But I do think you should include it because it's the umbrella term. All of these are going to be real numbers, but I do think you should include it. Notice it does say sets, plural, right? So that's why we're listing more than one, because some of them can have more than one. If something's a whole number, then it's all of them above it, right? A whole number is an integer, also a rational number, also a real number. 3.28, that would be a rational number and also real. 13/25 is a fraction, okay, so it's not irrational because it can be written as a fraction, or if you did it as looked at it as decimal, it would be terminating or repeating. This one would terminate. And so that is also a rational number and a real number. Again, I think you should include real here and here. And then 42 would be all of the above, except it's not irrational, right? So whole numbers and then all of its upper umbrella terms from there. Whole number, integer, rational number, real number. And yes, they did include natural number there. I'm not really requiring that, so probably can just leave that one out. Okay. Now, this then sets up an interesting debate. Which set of numbers is most reasonable for each situation? And then the first one they give us is outdoor temperatures. Okay, it really depends on how you look at this one, and I will try to make sure that I don't put something ambiguous like this on a test because you don't want me to do that, or I'd have to accept multiple answers, I guess. Because somebody might look at this and think, well, you know, the temperature doesn't go from 77 to 78 without passing all of those numbers in between, right? And in that case, we'd be talking about really a real number only, right? It could be rational, it could be irrational, I guess. You know, you could argue that, I suppose, and that would be one way. And you could just say the real numbers. And by the way, real numbers can be negative, of course, and temperatures can be negative, so that would apply. I don't think that's what they're going for here, because if I told you to look at the thermometer and then tell me what temperature it is, you would look at it and you'd say it's 77 degrees or it's 43 degrees. You wouldn't say it's 43.27098 degrees, right? So we tend to say it to the nearest integer. And yes, temperatures can be negative. We know that in Michigan. So that answer would be integers. I don't think it's as confusing in the second one, the number of beans in a bag. Let's just assume that the beans aren't cut into pieces, okay? So it's either 0 or 1 or 2 or 3 or 4 or 5, so that would be whole numbers. Integers and then whole numbers. And then this one says, determine whether the statement is true or false. If it's false, give a counterexample. All negative numbers are integers. Are all negative numbers integers? Nope. And a counterexample, maybe that's a term you've heard before, would be just an example that makes the statement not true. So, you know, how about a negative number that's just not an integer? How about a negative fraction of some kind? Negative 3/4. They use negative 2/3. The statement is false. Okay, now back to our little note sheet here. I meant to say from the top, I do think that you should take notes. And I haven't mentioned that in the first videos so far, but this would be probably a good thing to kind of jot down into your notes. Now, some people are going to figure out how to, you know, screenshot or, you know, save this or whatever. And that's okay. I mean, that's really up to you. You're in charge of your learning. But in a lot of ways, writing is learning. So if you copied this down, if you would have a spiral notebook and have a place designated for notes, that would be probably be your best chance of learning all of these numbers. All right, now moving down, inequality symbols. It is time, if you're not here yet, you need to get here real quick. And that is, it is time to be able to look at this by sight and know that this is less than. Look at this and know that this is greater than, okay? You probably, in fact, I've had, you know, every class reports to me that they've had a teacher who, you know, draws teeth on the thing. And I remember my teachers doing that when I was in middle school or whatever. They draw teeth on it, and it eats the bigger one to make them the same size. We're not doing that anymore. Okay, don't be drawing teeth. That was fun when you were younger. But you really need to be able to look at this by sight and know that less than, greater than, less than or equal to, greater than or equal to. This is going to be important for later. And then to that, another example. It says to write these fractions in order. Now you do have the use of a calculator, and you could turn these into decimals, and then you'll see their work as they do this. That's exactly what they do. And then it's a lot easier to just look and see which one is the smallest to the largest. It says from least to greatest, right? So your smallest one would be the negative 0.75. So as they list them in order, negative 3/4 would be first, and you can probably get it from there. Okay? And then lastly, I want to talk about absolute value. And basically, absolute value. If you don't understand absolute value, I'm trying to keep these videos at reasonable lengths. So if you need some brush up on absolute value, there's a good explanation on page 20 of your textbook, right before the lesson starts. It talks about what absolute value is, and it's basically the distance to a number from 0 on a number line. Okay. Now a distance is always positive, and that's what should happen. And I just want to show you a simple example of a common mistake. Because when it's the distance from 0 on a number line and the number we're dealing with is negative, obviously that's going to be the positive number of that. Okay, so the absolute value of negative 17 is 17 because there's 17 units between 0 and negative 17 on a number line. Okay, so then you quickly figure out, well, the rule would be then to just wipe away the negative, right? If it's positive, nothing changes. If it's negative, then you just wipe away the negative and it's positive, okay? And that's true, but be careful because when it's an operation, that's something different. So don't think that this, this absolute value, by the way, the vertical bars means absolute value. Don't think that means, oh, just change minus to plus. No, you need to do what's in there first. That would be 5 minus 2 is 3. And then take the absolute value of that and get 3, right? Don't just change minus to plus. That would give you 7. That's not correct. The absolute value of 5 minus 2 is the absolute value of 3, which is 3. And that takes us to our last example, which is to find the absolute value of each of these. Simply, this is a negative number. We're taking the absolute value of it. There is no operation here like I just demonstrated, so this would be just 2.5. Here you're taking the absolute value of a positive number. It just stays positive. Okay, thanks for watching. Thanks for tuning in, and good luck on your homework.